Okay, so for one of our assignments this week, like I did before on the other worksheet, I'm gonna go over this worksheet like we would in class, just talking over it. So if you've already turned it in, great. If you haven't, be following along and filling in the things as we go along. And then make sure you listen to the whole thing, because even if you did the assignment, you can make sure that your answers were on track or whatever. So remember for this lab, the breeding bunnies lab, we were looking at a population of rabbits in England that had a recessive trait that made them hairless. Okay, so the recessive genotype is going to be little f, which if you did the pre-lab, you should have identified that. And so those alleles for us, little f, were represented by 2 white beans. Okay, and then the 2 dominant alleles were 2 black beans. And then if they were heterozygous, it'd be black and white. Okay, so that's when I was pulling the beans out of the bag, putting them in the cup, all that thing. So moving on down here, I'll pause the video and finish the data table, and then we'll do the gene frequencies together. But first, and I explained this in the video for the activity, the number of big F alleles, you have to take this number of individuals, multiply it by 2, because there are 2 big F alleles in that individual, and then add the number of big F, little f individuals, because there's 1 big F allele in this individual. So in generation 4, it'd be 22 times 2, so 44 plus 6. 44 plus 6 is 50. And then number of big F individuals times 2 would be 4, plus 6 is 10. Okay? Okay, so looking through the number of alleles, if we're looking, the number of big F alleles stayed constant until generation 7, which we'll talk about in a second. It should have stayed constant. And then, so something fishy happened on generation 7, and literally the only person to blame is myself. So let's look at the number of little f alleles. And we started with 50. Remember, we started with 50 of both alleles. This one stayed constant because the big F alleles were, big F individuals were able to survive, but then the little f individuals died off. So that number quickly dropped, and then continued to drop, and then here it went up. So considering that's on this same generation, that's my fault. That's weird. It should have probably been 6 and probably been 50. And then it continued to decrease, and eventually, if we did it enough times, sure, we'd probably have 0 big or little f alleles in the end. But that would take quite a few generations. It still persists in the population, but the chances of getting a little f individual are incredibly unlikely. It's more likely that you'll get a big F, little f, which will survive and pass on the genes. So that the little f allele can stay present in the population for a long time without affecting the individuals. Okay. So now let's look at the gene frequency. So gene frequency, if we just think of what those 2 words mean, frequency is how often something happens. And so if we're talking about gene frequency, it's how often a gene happens. So it's the amount or prevalence of a certain allele present in the population. To calculate gene frequency of big F, you divide the number of big F alleles by the total number of all alleles. Okay? So this is saying how frequent it is in the population, round to second decimal if necessary. So to calculate the frequency of big F, you divide the number of big F alleles, which is 50 on generation 1, 50 divided by the total number, so 50 divided by 100 is, good job, 0.5. And this, since this stayed the same the whole way, your gene frequency of big F, is it going to change or is it not going to change? You might think, oh, well, because the gene frequency, or because the number of big F alleles didn't change, the gene frequency is going to change. But if we think about it, we have to take it by the total number of all alleles, which is decreasing. So for generation 2, we do 50 divided by 72. And for generation 3, we do 50 divided by 65. Okay, and the gene frequency, I'll go ahead and do the gene frequency of little f. Logic dictates that we take the number of little f alleles and divide it by the total number. So for generation 1, it'd be 50 divided by 100, which is 0.5. And then 22 in generation 2, 22 divided by 72 is 0.31. And then 14 divided by 64 is 0.22. Okay, so we'll go finish calculating these since we're kind of getting the hang of it. Okay, so here's the calculated gene frequencies of big F and little f. As you can see, the gene frequency of big F increased because as the gene frequency of little f decreased, then it made the black beans more prevalent, right? In the bag, it made the big F allele more prevalent in the population. Even though we weren't ever adding any, it was just more obvious in the population because we had less little f alleles. So if you look at the correlation between each gene frequency, you can kind of see that they are added together. You obviously would get 100% or 0.1 or 1.0 because the entire population is made up of these two alleles. Okay? And the graph looks pretty cool when we graph it, which we're going to do next. But I did put a box around generation 7 because I'm not going to include it because in our graph because something clearly went wrong. That's on me. I probably just counted like a white bean instead of a black bean or something. I don't know what I did. But obviously I messed up, which is fine as long as we recognized that it was an accident and it looked kind of funny and the data shouldn't look like that. Okay? So it should have stayed consistent here, but it didn't because I messed up somewhere. So I'm not going to include that in the graph that we will be doing on the next page. Okay, I lied. The graph is going to be on the next page under analysis. Here we're just talking about the post-lab conclusion questions. The first one says, refer to your hypothesis. Based on the outcome from the lab, do you accept or reject your hypothesis? And then explain. So a basic thing, do not, and I've told y'all this before, don't just say, oh, I accept it because it was right. That's not an explanation. So you'd say, I blank my hypothesis because, like, let's say your hypothesis was if you have a little f homozygous recessive bunny, in the winter they'll die off. Then they'll die off. That was your hypothesis. So you would accept your hypothesis because the little f allele decreased over generations or whatever. Okay? But there has to be an explanation there. Number 2 says, compare the number of alleles for the dominant phenotype with the number of alleles for the recessive phenotype. Okay, So the number of alleles for the dominant phenotype started off with 50. The number of alleles for the recessive phenotype started off with 50. So that's a good thing to note, that they both started with 50 alleles. But over time, what happened? The big F allele stayed constant because they weren't dying. They were reproducing and passing on that big F allele to their offspring. But the number of little f alleles decreased because little f individuals were dying off. Okay, so if you think about even the phenotypes, I'll just pull this up. In the first generation, you saw 36 furred bunnies, and then you only saw 14 furless bunnies, which might not seem like a lot, but it was obvious enough in the population that you'd notice that there were some furless bunnies. And then very quickly that started to decrease until there were no bunnies, furless bunnies left in the population. Okay, number 3 might read like the same question at first, but let's talk through it. So it says, compare the frequencies of the dominant allele to the frequencies of the recessive allele. Okay, so up here, the allele for the phenotype, big F, increased over, or big F stayed the same. You both started with 50. The little f allele decreased, but the big F allele stayed the same. And did that happen with the frequencies? No. So the frequency for big F increased as the population got smaller. The total population got smaller. And the frequency for little f got smaller, or decreased, we should say, because they were dying off, because the population was getting smaller. But I want you to note that big F increased and little f decreased kind of in the same proportion, right? So it'll make more sense when you do the graph. Okay, so number 4 says, in a real rabbit habitat, new animals often come into the habitat, which is immigrate, they come into, and others leave the area, emigrate, exit is how I remember it. How might emigration and immigration affect the gene frequency of big F and little f in this population of rabbits? So if we have new individuals coming in, then obviously that will affect the gene frequency. It won't stay consistent. It just depends really on how it's going to increase or decrease depending on which are coming in. It's probably going to be the case that it would make the furred bunnies stay, obviously, because they're doing fine, and the furless bunnies might leave and try to find a warmer place, even though it's not going to happen because they're in England. But they might go and leave in that pattern. So the furred bunnies might come in, furless bunnies might go out. So the gene frequency would probably still have the same general trend, but it might be more sharp or less drastic. And the second part of that question says, how might you simulate this effect if you were trying to repeat this activity? So we could actually test what would happen, and we'd have, our starting population of bunnies, and then each generation the little f bunnies would die off. But then maybe to simulate new ones coming in or different ones leaving, then you could change the amount of beans that you had in the bag. Okay, so after each generation, you could put like four black beans in there and that means that 2 furred bunnies came into the population, and see how that would affect it. Okay, number 5 said, did the genes of the rabbit population change over time? Okay, now I really want you to think about this question. So it says, did the genes of the rabbit population change over time? Did the genes change because we had a fur bunny and we had a furless bunny? Did anything with that change? No, we just started to see more furred bunnies. Did the furless bunnies ever change their genes and turn into furred bunnies? No, they can't do that. They just died. So if to someone that has not taken biology with me before, if you look at this population of bunnies, people might be like, oh, well, those furless bunnies just like grew fur. But can that happen? No. The furred bunnies are becoming more prevalent because the little f furless bunnies are dying off. So did the genes of the rabbit population change over time? The individual genes did not. But their prevalence, or how often they were in the population, their frequency did change. So, like I said, if you have this population of bunnies, and at first we had 14, up here we had 14 furless bunnies, and then the next generation comes around and you're like, oh, well, there are way less bunnies. Like maybe they realized it was bad and they grew fur. No, they died. And that gene wasn't as prevalent or frequent in the population. Okay, number 6 said, predict what the population of bunnies would look like over the next few generations if conditions stay the same. So if the weather stays the same and the little f bunnies are dying off, if no bunnies are emigrating or immigrating, if the conditions all stay the same, what would the population look like over the next few generations? Okay, so let's pull back up our data. So if we're looking, we have 4 little f alleles left. So there is a chance, a small chance, like it happened here, where it was 0, 0, 0, 0, and then miraculously I got 1 little f bunny, 1 furless bunny. That might happen if you kept doing this. You'd see that trend where you get 0 furless bunnies for a couple generations, and then maybe chances are the Punnett squares line up correctly, and you get that 25% chance of you having the recessive genotype, and then eventually it would die out. So if conditions don't change, you may have a couple furless bunnies, but they would die off. Making the entire population furred. Okay. Number 7 says, what would happen to the furred bunnies, so this population of bunnies up here, if we took them to a hot climate, say Arizona, okay? And think about the entire population, not just the individual bunny, okay? So if we took, let's say, not this population at the end, let's say we took the beginning population with 50 and 50. In this case, in this new environment, which bunnies are going to be better suited? The furless bunnies are going to be better suited because they can survive in the hot climate, okay? So if we're thinking about the entire population, not just the individual bunny, because yeah, like an individual furred bunny could like lose some of its fur, but it's probably going to end up dying, okay? So the furred bunnies are going to die off this time, and the furless bunnies are going to survive and reproduce. So over a few generations, the population would have greater frequency of little f furless bunnies. Okay. So this question is really important because it goes to show the importance of thinking about the environment or the local environment. So it's not just that the furred bunnies will always do good and they're always the best ones. It's the ones suited to the environment. So in this case, in England, yeah, the furred bunnies did better, but in a different environment, that trait might not be beneficial. Okay, now on to our graph. It says we will be graphing the gene frequencies. We will need a double line graph, one for each allele. Be sure to include a key and label all axes. Okay, I'm gonna do this on a separate little part so that I have more room. So 1 second. Okay, so this is for the graph. It wasn't a number, but it was the first thing under the analysis where it said make a graph. So we're going to make our graph using our gene frequencies, which are the highlighted columns. So since we have 2 gene frequencies, we're going to have 2 lines. It would be impossible to do them on the same line. Okay, so on our x-axis down here, remember dry mix. Let me write that at the top. Okay, so the x-axis has the independent variable or the manipulative. So the thing that is changing over the experiment. So in this case, as most often, if we have time, it is going to be the independent variable because it is changing. But in this case, it's not measured in like years or minutes. It's measured in generations. Okay, so we have the first, second, third, fourth, sixth, eighth, and then the 10th generation. Okay, and then the y-axis has the dependent variable, which is the response or the thing that we were measuring. So in this case, it is the frequency. Of genes. Okay, so what we're going to do first, since we have 2 lines, well, let me label this, hang on. Okay, as you can see, I went and labeled 0.1, 0.2, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and then 1 whole, which would be 100%. Okay, so we're going to need 2 different colors. Let's do red for big F. So I'm going to do my key over here is in red. Okay, and so then we just start going. So in generation 1, the gene frequency was 0.5. In generation 2, the gene frequency was 0.69. In generation 3, the gene frequency was 7.8 or 0.78, sorry. Generation 4, it was 0.83. Generation 5, it was 0.89. And then it stayed 0.89 for a while. This is generation 6. Generation 7, remember we're omitting. Generation 8 stayed at 0.89. Generation 9 is 0.89. And then generation 10 is 0.92. So it went up a little more. Okay? And then we connect them. Beautiful. Now let's do the same, but with the little f allele and a different color. Okay, so we start off at 0.5 again, so I'm just going to do another dot there, but then very quickly the numbers got different. In the second generation, you had 0.31. In the third generation, you had 0.22. Fourth generation, 0.17. The fifth generation, 0.11. Sixth generation, 0.11. We skipped the seventh generation. Eighth generation, 0.11. Ninth generation, 0.11. And then the 10th generation was 0.08. So let's do... Okay, so that looks pretty good, if I do say so myself. So, if you are, we forgot one thing. We forgot our title, which I'm going to put over here. So this is just the gene frequencies of a population of bunnies over 10 generations. That is a perfect title. There's our title. Okay. But if you're looking at the graph, we could kind of predict it would look this way because of the numbers. So remember, if you added them up together, they equal 0.1. And so this is what I was kind of saying on that other question where they increase or decrease at the same rate. So these, if you did a little line right there and mirrored them, they'd be perfectly symmetrical because as this one went up, this one went down at the same rate. Does that make sense? So that's why we have this wishbone looking graph. Okay, so on to the next problem on the analysis. Okay, so we can finish answering these questions using the table and the graph. So number 8 says, what happened to the little f allele? Did it completely disappear? It did not completely disappear, so no. It exists in the population, though, because there weren't any furred bunnies. It exists in the population in the heterozygotes because they're big F, little f, and they still have the little f allele, but they don't die off. No, little f still exists in the heterozygotes. Number 8 says, explain what would happen to the rabbit population if the hairless gene was dominant. Okay, tricky. Everything else stayed the same, so the original population, the place that they're at, England. So then if the hairless gene was dominant, then all of these individuals in the first generation would die off, and you'd be left with the little f individuals surviving. So that population is already pretty small, because even though you started off with 50 little f alleles, most of those little f alleles were found in these individuals, which big F, little f, if the hairless gene is now dominant, all of these individuals would die, all of these individuals would die, leaving you with only the little f individuals. So the population would drastically decrease, leaving only little f individuals to survive and reproduce. Okay, number 10 says, what would happen to the frequency of the little f allele if it was not harmed? So that's, or if it was not harmful. So that's saying the frequency of the little f allele, if we didn't have to kill them off each time, it would stay the same. Because the main reason that the gene frequency was changing was because we were killing off that harmful gene with the little f individuals. Number 11 says, how are the results of this simulation an example of natural selection? So if we think about the word natural selection, it's just where nature is selecting who lives and who dies, basically. So because the little f individuals were not suited for the environment, they died and didn't pass on their genes. The big F and big F little f individuals were suited for the environment, and they get to pass on their genes, making furred bunnies more frequent. Okay? So, if you made it this far in the video, good job. This is one of your assignments for the week, just to listen to this video. So go ahead and email me, just saying in the subject line that you watched the Breeding Bunnies video, and you'll get a 100. I hope that me recording these videos is helpful to you, since we can't really go over and grade together the assignments.